Okay, so this is where we left last time. So we have to discuss about two integral equations. One is Helens and another is Pollington's. Pollington's you have already done. So we'll discuss about the Helens equation today. So what we have here is the programming exercise in class. Means we'll discuss about how to do programming for the Helens equation, and the one I'm considering here is the exact kernel. So the assignment or the programming exercise, your homework would be for the approximate kernel. So this exact kernel is much more complicated. So I'll discuss this in the class so that you can easily do your programming exercise homework for the approximate one. So this is the Helens integral equation. What you have in the left hand side is 1 by pi minus h to h. 2h is the length of the wire dipole antenna. Iz is the current density which you are supposed to find using the MoM. K is the kernel of this integration, and K is represented like this. And K is an integration from minus pi to plus pi, and you have exponential function here. And denominator, you have this function here. So you can derive this, but will not derive this. We have done the simple case for the Pollington's one. Helens also you can derive it, but assume that integral equation is given to you. Since you want to learn MoM, the integral equation is given to you. You want to apply MoM and try to find out what is the unknown current density on the wire dipole antenna. And on the right hand side, you have this term here. One is cosine function and is sine function. So now if you have an integral equation, exact kernel of Helens equation like this, then how do you solve using the MoM, no? Method of moments? Like last time, we'll use piecewise constant function, which is also called as pulse function. And the source excitation is magnetic field source. And you'll use weighting function as a delta function. That means you are doing point matching methods. At the starting, you will define Z as a symbol so that you can do integration. You have Z here. Z here, you want to do integration. So I will define this as a symbol. And you have already done some of the exercise, programming exercise. You have already used this. I have already seen that many of you use this as a symbol. And first thing, let's define the radius of the cylindrical dipole, and it's very small. A is equal to 0.0065 meter. No? So this one typical value of radius of cylindrical dipole will be doing for our programming exercise in class. The half length dipole, this is half the length of the dipole. Total length is 2h, it's around 0.05 meter. You can observe that this h is much larger than A. That was one of the conditions for a thin wire approximation. Then operating frequency, you define it's around 1 GHz. So we are not working at the megahertz frequency, we are working at the gigahertz frequency, which is usually we do for the analysis for microwave frequency antennas and all. So high frequency antennas, we are not going to consider low frequency case. Usually we use antennas at high frequency so that it has many advantages. Then velocity of light is, you all know, it's c is equal to 3 into 10 to the power 8 meter per second. So all this constant you can define at the starting of your program. Then permittivity for free space is this, epsilon 0 is 8.85, 10 to the power minus 12, and permeability for free space is 4 pi into 10 to the power minus 7. I think it's good to remember all this constant. Sometimes you forget it, then you cannot find. For example, if you want to find the wave impedance for free space or intrinsic impedance for a free space, you can use this value of mu naught and epsilon and you can find it out. So you need to remember this constant. If you don't remember, we will provide in the exam, but it's always better because you are a student of this course and these are some natural constants. You can remember it. So eta becomes 377 ohm approximately. And epsilon r is called the relative permittivity, and it's equal to 1 for year, and angular frequency you can define as 2 pi f. Propagation constant you can define as 2 pi f square root of epsilon r divided by speed of light. So now if it is free space, epsilon r will become 1. If you have other medium, epsilon r, depending on that, propagation constant is going to change. So like last time, we'll use the number of segment, number of pulses total number of segments, capital N is equal to 9, and odd number, so that I can find out what is the input impedance at the center of the antenna. We have upper arm and lower arm for the dipole antenna. Segment length is delta Z. How much is the size of your segmentation, delta Z? Total length is 2h. Total number of segment is capital N, so 2h by capital N. And we also use match point. So you use the delta function. So point matching. What is the observation point Zm is at the center of the discretization mth segment. So you find it, we have already discussed in the last class, m minus half delta Z minus h. M can go from 1 to 3 up to capital N. So now let's look at the discretization of AMN, or let's say your Z matrix. Usually we call it Z matrix. So how do I do the discretization of the Z matrix, B matrix, and how do I find the current unknown coefficient I? So I need to find Z, B, and find what is I once I know Z and B. So this is your Z matrix. So Z matrix calculation can be from the integral equation. Let's look at the integral equation you have here. This is the integral equation. This is the left hand side of the integral equation, right hand side of the integral equation. So right hand side will give you the B matrix, left hand side will give you the Z matrix as well as your I vector. So I vector will be I1, I2 up to In. That's what we are supposed to find. Remaining terms here is basically gives you a Z matrix here. So now if I want to find Z matrix, then I have to do integration 1 by pi integration of minus h to plus h. But now this is for a particular basis function. Particular basis function is a pulse function. Pulse function is non-zero only over that interval, and outside that interval it will become 0. So pulse function has a range or span from Zn minus delta Z by 2 to Zn plus delta Z by 2. We're considering the nth pulse function. Nth pulse function will be non-zero from Zn minus delta Z by 2 to Zn plus delta Z by 2. So this integration, when I replace this Iz by In Bn for the nth basis function Bn, Bn will have only value of 1 from in this interval. All other outside that interval will become 0. So this integration from minus h to h will be reduced to this integration. And what do I have? I have a kernel k here. What was the kernel k? Let's look at the kernel k. The kernel k is this. The kernel k we have for the integral equation was like this. So now I have to do discretization of this. One is for the source and one is for the observation. Source is n here. N is the running index for the source. What is the running index for the observation? That was m. So here, look at this expression here. What is the variable which is dependent on the observation point is your z here. Z dash is for the source. Z is for the observation. So when I consider the observation for the mth point, then this Z will become Zm here. So Zm minus Z dash. Z dash is for the source, and it has the source is over the interval Zn minus delta Z by 2 to Zn plus delta Z by 2. So this dz integration is over this interval, nth interval. And we have observation at Zm. So you replace this Z by Zm here in the kernel of the integration. So that is the only thing you have to do. Z by Zm. And this integration from minus h to plus h should be over the nth interval of the pulse function. So this is your Z matrix. So now you can actually, this is a double integration here you have here. The double integration you can easily do using the command and MATLAB integral 2, and you can do the integration and you can find the first row. Then from there you can find out all the elements of the matrix. So I have told you a technique to find out the upper triangular matrix first. Then you take the transpose of that, sum it with the matrix itself. You can create the matrix. So what do? You just find out this upper triangular matrix. First, you find out just this first row of the matrix. Then you can fill up all this thing. You can see that this is same here, this is same here, this is same here. You fill up this upper triangular matrix. And make sure that diagonal elements is divided by 2. So when you take transpose of this, let's call this is A matrix or Z matrix. Let's call it A matrix. So you sum A matrix plus transpose of A matrix, then all these things will come down here. So it will fill up this lower triangular matrix also, and diagonal element, since you are summing a plus a dash, so this will become twice, then it will become just a11, a11, a11 here. So you don't have to fill up all the matrix. You just find out the first row of the matrix. You just fill up the upper triangular matrix, take the transpose of it, then sum it with itself. You get the Z matrix. So that's a very simple way of doing the thing because it will save your computational time. One point to be noted here: this diagonal element is always same. You just calculate this first diagonal element. You can fill up all the diagonal elements here. Why is that so? Let's go back to the expression we have for the A matrix here. AMN here, actually you look at the AMN here, the only term which is dependent on the dependent is Zm minus Z dash here. All other terms are equal. No? So only Zm minus Z dash is dependent on the source and observation point. But let's say if your source and observation point are at the same interval, then this Zm minus Z dash will be always equal. So that's why the diagonal elements are all equal here. So we got the Z matrix. We also need to find out the right hand side. Now, what do I have in the right hand side? Right hand side, I have this term here. This will give me the B matrix or B column vectors. So now in this case, for the Heron's integral equation, the B column matrix has two parts. One is cosine function and sine function. So we need to have two vectors here. For the first vector, see, basically we are making an observation point at what? Zm. So this will have Bm, will denote it by Bm is equal to cosine of Kzm, and M can have values 1 to 9, so cos of Kz1, Kz2, and so on. This term will have this, and this term will also have Cm here. Cm here, you assume that B naught is 1, then it will become minus J by eta sine of modulus of Kzm. Zm can be 1, 2, 3 up to Z9. So we have right hand side, we have left hand side. We want to find out what is this I vector. We can do that. So left hand side, what do I have? In into AMN is equal to, you can write ZMN also, it's okay. Then right hand side, what do I have? Xi naught, this is Xi naught, then cos of Kz. Xi naught, cos of Kz I have represented it by Bm plus second term I have represented it by Cm. So now if I want to find this In here, I know all other terms. I can find out In is Xi naught Amn inverse Bm plus Amn inverse Cm. I will denote this term here as Dn. This term here I will denote it by Sn. Just a short notation. Huh? So then I can find out In as Xi naught Dn plus Sn. Okay, so one more thing here is I do not know what is this Xi naught here. Xi naught is a unknown constant. How do I find out this unknown constant? See, basically at the ends of the dipole antenna, you have an open circuit, so there won't be any current flowing there. Current would be 0 at the end. So the ninth component, I9 should be equal to 0. The current at the ends of the antenna is 0. So in that case, look at this equation here. This here. For the ninth component, so ninth component n becomes 9. So this current I9 is 0 because that's the end of the dipole. You have an open circuit, current cannot flow there. So this term is 0, I9 is 0, so equal to Xi naught D9 plus S9. So from here, you know what is D9, S9, you can find out Xi naught. So Xi naught is minus S9 by D9. That's how you find this unknown arbitrary constant Xi naught. So that's how you solve the Helmholtz integral equation exact form. So now basically the programming exercise 4 would be a simplified version of what we have discussed just now. Let me briefly discuss what is this programming exercise 4 homework. You have to write a MATLAB program to find the current distribution and input impedance of a center fed dipole, but you consider the Helmholtz equation. Here it's not the exact kernel, it's a reduced kernel, simplified version. In the reduced kernel, the kernel K is a much more simplified one. So you have this equation left hand side 1 by 4 pi minus x to h, Iz k dz dash. We call this K as kernel. And here the kernel, you look at the kernel here. Kernel here is after you apply the thin wire approximation, and it's very simple one. The difficult one we have already discussed in the class. For your homework, this will be the reduced kernels. Right hand side remains the same. Only the kernel has been reduced kernel. So your programming exercise homework would be much more easier than what we have discussed in the class. Here we also use pulse function. We call it piecewise constant function, and excitation is magnetic field source excitation. You can do point matching. That means your wetting functions or testing function is the delta function. As usual, you define Z as a coordinate, as a symbol, so that you can do integration, direct integration in MATLAB. Radius of the cylinder is same like last time. A is this. Height is this. Same as last time. Operating frequency is 1 GHz. And speed of light, you need to define constant speed of light, epsilon 0 for free space, mu 0 for free space, intrinsic impedance for free space. Then relative permittivity of air is 1, then omega is 2 pi f. Once you have defined f as 1 GHz, you can find out what is angular frequency. This will be required when you write the program. That's why k is defined as 2 pi f square root of epsilon r divided by speed of light. Number of segments is 9, like last time. We take an odd number so that we can find out what is input impedance at the center of the wire dipole antenna. Delta Z is total length of the dipole divided by total number of subsections. The max point, observation point, is at the center of the emit segment, and that is m minus half delta Z minus h. M going from 1 to capital N. So now discretization for the Z matrix. How do I do it? This is a reduced kernel now we have here. So you can do discretization 1 by 4 pi Zn minus delta Z by 2 plus Zn plus delta Z by 2. This is the exponential term, this term here. You have just replaced Z by Zm here because we are making observation at the emit center of the emit segment. Since we have only one single integration here, you can just use integral. So last case when you have double integration, you have used integral 2. Now you can simply use integral, single integration. You just find out the first row of the Z matrix and you can fill up the matrix like last time. So the first row is this you can see that this is same here. You can just fill up, this is same here, this is same here, and so on. You can fill up the upper triangular part of the matrix and just make sure the diagonal element is divided by 2, so that when you take transpose of this matrix to fill the lower triangular matrix, diagonal element becomes the original value of the Z matrix. And you know that diagonal element is same because this term here Zm minus Zs is actually same for all the diagonal elements, because your observation and source are in the same segment of the dipole wire antenna. You fill up the matrix. This is the matrix you have, and right hand side you can calculate like last time. Cm will be minus j by 2 eta sine of kzm, modulus of kzm, z1, z2 up to z9. Similarly, bm would be cos of kzm, kz1, kz2 up to kz9. Now you can write the matrix equation from the integral equation. We have converted into matrix equation. It will become In Zmn equal to xi naught bm plus cm, and all the diagonal elements was equal because your source and observation are at the same location. Distance between them would be same, and that was the only variable you have in the integration for Z matrix. And you can find out the unknown current density by inverting Z matrix or A matrix and multiplying with this what you have in the right hand side, and denote this term here by the dn, short notation, this term by Sn. Then finally you can find out this xi naught is a unknown constant you have here by applying that at the ends of the dipole antenna. Current should be 0 because we have an open circuit here at the ends. There won't be possibility of flowing current at the open end. So from there you just plug it in this equation. I9 is equal to epsilon xi0 dn plus d9 plus s9, and you can find out xi naught s minus s9 by d9. This is your fourth programming exercise. Okay, so that's how you find out the current distribution on this dipole wire antenna. So this is the upper arm of the dipole wire antenna. This is the lower arm of the dipole antenna. So now, once you have the current distribution, I have been telling you that you can find out all the antenna parameters like radiation pattern. So how do I find the radiation pattern of the antenna once I know the current distribution? So this is what we are going to discuss here. So you look at it. Let's say P is the observation point here. P is the observation point here. I have noticed that there's some delay. So this P is the, when we do the recording, no, in the recorded version, there's some delay here. So this is the point P here. This is observation point, and this is in the far field of the dipole antenna. So this is the dipole antenna. We are considering the radiated field in the far field of this dipole antenna. And most of the time, antenna engineers require far field radiated power. That's a usable field that will be, we can use at any far away distance. Total length of the dipole antenna is 2h. So you have, one is observation, one is the source. There are two variables here. All the source variables are denoted by with a prime coordinate. For example, z-0, z-. Let's assume that there is a source here at this point at the location z- from the origin. Assume that there is a source here, and we are making observation at point P here. So now in the far field, this line you have from the source point to the observation point, or this line you have from the origin to the observation point, they would be in a parallel line. As you go farther and farther away from the dipole antenna, the line which is extended from the origin to the observation point and line which is extended from the source to the observation point, they would be parallel lines. So now they are not of equal length. They are almost equal if you are very far away from the antenna. But when you consider the phase of the antenna, even if there is a small changes, phase is going to change. See, basically your phase, as I've told you in the previous semester also, phase variation is from 0 to 2 pi, but your distance variation is from 0 to infinity. As you go further and further away from the source antenna, when you make an observation, the distance of the observation point from the origin, see, basically source is here, you are making observation at this point. This distance and this distance here from the origin to the observation point, they would be almost equal for the amplitude term of your electric field. But for the phase term, there's a slight change here. You just draw a practical vertical, you draw a vertical line from this here, from this source point to this line here, which makes an angle 90 degree here. How much this is length? This length, you know that this is z dash. The location of the source point is z dash from the origin. How much is this? Let's say this angle is, let's say mu or something like that. So then this is right triangular angle. So if you want to find out this is the hypotenuse, this is the vertical line, this is the base. So I can find out z dash cosine of mu, this angle here. So now if you compare this length and this length, when you are in a very far away distance, this line is slightly longer than this line. By how much? By this term here. So this line here would be approximated as this line, if I call it rho minus z dash cos theta. So this would be actually theta here. So this line is slightly longer than this line, which is actually the actual distance between the source and observation point. Actual distance between the source and observation point is this line here, and this line is shorter than this line, which is the distance between the observation point and the origin. So distance between the observation point and origin is rho, if we call it. Then if this is z dash, this is z of cos theta, z dash cos theta. So r would be, if you call this as r. Distance between the source and observation is r. Distance between the observation point and the origin is rho, then r will be rho minus z dash cos theta. This theta is the angle. So let us try to find out the far field radiation of the dipole antenna. So as we have a lot of discussion in the previous semester also, it's always easier to find the electric field from the magnetic vector potential. Once I have the magnetic vector potential, I can find out the field easily. And finding the magnetic vector potential from the current density is very easy, because current density and magnetic vector potential has the same direction. So If you know the direction of current for the current density, you don't need to find the direction of the magnetic vector potential. So you can have the same direction for magnetic vector potential. So finding the magnetic vector potential is like finding finding a scalar quantity. It's always easier to find a scalar quantity than a vector quantity. So look at this. The dipole is a metal wire antenna. So you can assume that current is flowing in this wire antenna. So it's along the z axis. So current is flowing along the z axis. Magnetic vector potential also follows the direction of current density. So Az would also only have z component. So you can find Az as, usually we put it mu by 4 pi. I have put mu later on. So you can have mu by 4 pi here, then you don't need to put mu here. So if I assume that Az is 1 by 4 pi minus h to h, Iz exponential minus jkr by r dz dash. I'm not assuming it. This is the formula for finding the Az from the current density Iz. From the MoM, I know what is Iz. So I can find out what is Az now. Just before that, let's assume that this is in the far field of the antenna. In that case, I can replace this r by rho here. I have told you the amplitude term r can be replaced by rho, but the phase term here, since phase is varying from 0 to 2 pi, it will very, very fast. No, phase will very
Hello, sir.
Hello, sir.
Hello, I think sir is not in class.
Yeah, sir has left, I think.
Internet may be disconnected from sir.
छुट्टी हो गया, चलो सर.
छुट्टी हो गया क्या?
ये सब रिकॉर्ड होता है.
There is some issue with the network. Everyone is facing the same issue, I think, in other class also. Let me see. Can you see the slide? So we can actually find out the magnetic current density. What is that? Just 1 second. So we can find out the electric current density from the MoM. From there, you can find out the magnetic vector potential. And you need to worry about the phase term here. Phase is changing very fast, so you have to take care of the distance between the observation point should be actually rho minus z dash cos theta. We have already discussed, and amplitude can be replaced by rho. So now when you do the integration over dz dash, look at this term here. This exponential minus jk rho term is independent of z dash. So your integration would be only for exponential jk z dash cos theta dz dash from minus h to plus h. And once you have the magnetic vector potential, you can find out the electric field. Electric field will have only theta component, and it will be simply minus j omega mu a theta. So I have not put mu here. That's why we have mu here. So how do you find electric field once you have the magnetic vector potential? You do minus j omega a theta. No? So this is what time bearing case. In the time bearing case, time harmonic fields, you replace del by del t by j omega. We have done a lot of discussion on that. So now a theta, how do I find? I have az here. How do I find a theta? A theta, you can see here. This a theta is basically your projection of az along the theta direction. And what is the angle between z and the theta? So angle between z and theta is, this angle is theta, and angle between the z direction and theta will be theta plus pi by 2. So az cos of theta plus pi by 2 is sine of theta minus sine of theta, because you know that cos of, see, this a theta would be az cos of theta plus pi by 2, because angle between the z component, z unit vector, and theta unit vector is theta plus pi by 2, and cos of theta plus pi by 2 will become minus sine of theta. That's why minus minus is gone. You can find out e theta as j omega mu sine theta az. This will give you the theta component. So once you have az, you can find out e theta, which will give me the far field radiation pattern of this wire dipole antenna, and I can find out az from the iz. Once I have iz, then I can find out az from this relation you have here. Okay, you can further simplify this expression for e theta. E theta is what? J omega mu sine theta az. Just replace az by this expression you have here. Iz exponential minus jk rho, this term here. Okay, so you can do simple integration of this one. This is the exponential function. So you do the integration, exponential function. It will give me exponential jkz cos theta divided by jk cos theta. And it's going from minus h to h. So you plug in minus h and minus h. So what does this look like? So you multiply and divide by 2j here. You multiply and divide by 2j here, then it will become sine of hyperbolic cos of theta divided by kh cos theta. You can replace this. You can simplify this. This will become 2j when you multiply it. When you multiply 2j here and 2j here. So basically, I want to convert this exponential function into a sine function. So I multiply by 2j here. I also divide by 2j here. In that case, this 2j and this term here will become sine, and this 2j here you can simplify it. Finally, this looks like a sinc function. Sine theta by theta is a sinc function. Okay. So after that, we'll move on to a new topic. So that is called spectral domain MoM. Maybe I should stop here.